Right, so what we covered basically, I'm just going to go through everything that we did. We talked about circuits in real life scenarios in industries. You don't have purely capacitive, purely resistive, purely inductive anymore. What we mentioned, if it is purely resistive, there is no phase angle between voltage and current. So voltage and current are in line with each other. So that's voltage. Current in line with it. And current a little smaller than voltage usually, because that's usually the case. Not always. So that's for purely resistive circuits. And for inductive circuits, or purely inductive circuits, voltage, which one's leading? So if we remember that mnemonic, Sybil. So if it is inductive, we just look at this part. This is L, inductive for L. Voltage is in front of current, so voltage is leading current by 90 degrees. So if that's voltage as reference, current is lagging 90 degrees, or voltage is leading 90 degrees. When we say leading is anti-clockwise, clockwise is lagging. And for capacitive, purely capacitive circuits, if that's voltage, again looking at that, if it is capacitive, current is leading voltage. So current would be up here by 90 degrees if it is purely capacitive. Now, like I said, in reality, there's never purely resistive, inductive or capacitive circuits. So for these, all the phase angle, which is 90 degree here, it's never going to be 90 degrees. So it's going to be always between 0 and 90 degrees, either negative or positive, depending on which one is prevailing. If it is capacitive, then it's positive. If it is inductive, it's negative, whatever degree, 60 degree, 30 degree, whatever. So now if I go to the scenario of having actually all three elements in series, R.L.C. circuits. Normally, if it was a DC circuit and you had only resistors there, R1, R2, R3, and your voltage. Kirchhoff's voltage law stated that if you add all the voltages in the circuit, V1, V2, V3, it would sum up to the voltage of supply. The supply voltage would be equal to the sum of all these voltages. Now in AC, because these elements are reactive components, we talked about reactive components, they're falling on the y-axis, or the imaginary component of the Cartesian diagram. Then if we say this is VR, and that's VL, and that's VC, if you add them together algebraically, they won't sum up, they won't add up to the voltage of supply, the S supply voltage. It won't be equal. You might have, for instance, you might have 100 volts here, 50 hertz. This might be 50 volts. I'm just saying it randomly. Obviously, it all depends on the size of these elements. It might be 50 volts. This might be 300 volts. That might be 200 volts. And as you see, it's a lot bigger than that. Your own source. It's just because it's imaginary and it's not real component. real value. It's a real component, it's not a real value in the sense of real numbers. So if I just get rid of the values here. Now, what's constant in series? Remember what's constant in series? Current. Current is constant. So this is the way you draw phasor diagrams in any circuit. If it is parallel, you consider current as your reference, and then you draw the rest of the diagrams around it. If it is series, you consider your current as your reference, and you draw the rest of it around that. When we say reference, that means it's on the x or horizontal axis. Now, looking at that voltage of the resistor, we said if it is purely resistive, just the resistor itself, voltage of resistor VR would be in line with current. So I will just draw a line a little bit bigger than current. Like we said, voltage is usually bigger. So VR would be there in line with current, and that current is the current of the whole circuit. So from that, we said voltage of the inductor is leading current. Inductor's voltage is leading current. So I want to draw the VL be here, and VC voltage is lagging current, or current is leading voltage. So current is here and voltage is lagging down here, VC. Now, to find the overall voltage, the voltage of the supply, you have to basically add all these three vectorial sum, the vectorial sum of all these. To do that, the first thing you do, you get rid of this. You've got two vectors or two phasor diagrams 180 degrees away from each other. You take one of them away from the other, the smaller away from the bigger. Usually you'll find VC is smaller than VL, or even XC is smaller than XL. But it might not be always the case. If this is bigger, your resultant will be down here. If that's bigger, the resultant, the overall resultant will be positive. So VC taken away from VL, that's VL minus VC point. So it basically shifted this up as VL minus VC, and then add these two vectorially. You draw a parallel line to VR and another perpendicular to VL minus VC. You just connect the points from 0 to that. And that is your VS, or supply voltage. The phase angle is the phase angle between voltage and current of the whole circuit, the overall phase angle. How do we actually calculate this? Now, there's three methods to do this. One method is just draw it to scale. Let's say every centimeter or every millimeter is 1 volt, whatever, 100 volts, depending on how much you have. You can have two scales, one for voltage, one for current. You don't have to have the same scale for voltage and current because they're different ratings. And then when you draw this, measure that with a ruler, times it by your scale, you find the VS, and then measure that phase angle with a protractor. And that's one method. First method with actually drawing everything to scale, which is not what we want to do. This is like a little bit lower level, level 2 or 3 that do that. So the second method is using Pythagoras. Do the same thing, but we actually, you don't have to do it to scale. you just do a sketch of that. And to find this, you look at this right angle triangle. So you can write the formula for Vs using Pythagoras as square root of VR squared plus, that is VR minus VC squared. And that's how you find the amplitude of the voltage of supply. That's also called, when we get to the polar notation, that's called the modulus of the voltage. And this phase angle is called argument. How do we find the phase angle? You can say theta, you can say phi, that would be however you name it, doesn't matter. So theta, you can use trigonometry to find that. Inverse tan, that's VL minus VC over VR, and that will give you the phase angle in degrees. We call this voltage phasor diagram or voltage triangle. And then from that we said, if we divide the whole thing, all the phases, all the vector diagrams by current, you get to impedance triangle. And the way we do that is VR using Ohm's law, V, that triangle, remember that. So V over I is R. So if I just changed R to XL, it would be the same scenario. V over I would give you XL if you want to find that one. If you only got XL. And if you only got XC, it would be XC. But if it's all together like this, V over I would be Z. Because we're not dealing with just resistors or inductors or capacitors. We're dealing with all three of them, and that's called impedance. So, now, for VR itself divided by I, you would have a straight vector on the horizon, again horizontal axis, which is R, because VR over I will give you R. This part, VL over I will give you XL. Now, if you've been given L and C, or L and C, you have to straight away convert that to XL, and this one to XC, because the measures you have here, L is measured in henries, C is measured in farads, or multiples of them, millihenries, millifarad, microfarads, and all that. So you have to convert them to a value, a unit that is measured in ohms, so it's similar to the rest of the circuit, and then we can measure the impedance, because impedance is measured in ohms. So XL, to find XL, the formula is 2 pi f L. L is the inductance in henries, so if it's not in henries, you have to convert it to henries to get the XL in ohms. And F is frequency has to be in hertz as well. If it is kilohertz, again you have to convert that to hertz. And XC is 1 over 2 pi FC. Same, frequency has to be in hertz, C has to be in farads. If it's not, you have to convert that to get the XC in ohms. And that's the first thing you do. Any circuit you see is immediately convert that to XL and XC. Then you get VL divided by I will give that's your I, which is going through all the circuit. I is constant. Gives you XL, and VC divided by I will give you XC. Now, if you get the overall resultant of this phasor diagram, you'll find Z, or impedance. So, again, we take XC away from XL, and that's XL minus XC point. And the resultant between R and XL minus XC vector is this, and that's your Z. And this is your, again, phase angle. Phase angle, whether you find it in here or there, it should give you the same phase angle, with the same value. And again, you use Pythagoras to find this Z is square root of R squared plus XL minus XC squared. Now, if you happen to have XC bigger than XL, and you said XL minus XC or XC minus XL, it won't make any difference, because when you square it, it'll be positive. And again, for the phase angle, you can use inverse tan, opposite over adjacent. Opposite is opposite is XL minus XC. Over R. And that is your impedance triangle. So we basically found in two methods, two different methods, drawing it to scale and using Pythagoras, the voltages and impedance of the circuit. Now, from that, before I go away, before I wipe this, we said if you have the voltage, in this case we divided it by current to find impedance. If I times this thing, I'm not going to redraw it, the same thing, times current, you'll get to the power triangle. Then VR times I will give you P, which is true power, and VL times I will give you VL times I will give you Q. I'm just going to name this QL. Overall, you'll only have one Q, which is the reactive power. But I'll just name that because we have two elements of reactive power. One element is the inductive, and the other one is, if you times voltage VC times current will give you the QC part of it, the reactive, capacitive reactive power. So to avoid all that, capacitive reactive power, which sounds silly, and inductive reactive power, basically, when you take this away from that, and you have overall just one Q, which is here, just name it QL minus QC, then that is your overall reactive power. and the resultant between this and the true power, if you draw arrow lines and join these two points, that is S, it's called S, and that's apparent power. Again, the phase angle would be the same method, and it should be the same. If you found it here and calculated it here, it would be the same. Again, S using Pythagoras would be P squared plus Q squared. Q is QL minus QC. And phase angle is, again, you can use inverse tan. Opposite over adjacent, that's Q over T. Now, the reactive power, I think I didn't mention this last week, the reactive power is measured in volt amp reactive, and that's how they write it, or kilovolt amp reactive. This is measured in watts, and S is measured in volt amp. So volt amp is the unit. So the unit for reactive power is volt amp reactive, for true power is watts, and for apparent power is volt amp. It can be multiples of it, kilovolt amp, it usually is megavolt amp, kilowatts and all that. And we talked about power factor briefly. We said basically true power is how much you use, apparent power is how much you pay. To bring this down, it's called power factor correction. So you're trying to correct it, so you pay as much as you use. And that is the cos of this angle is your power factor. So here power factor is the same as saying cos of that phase angle. And that's where the power factor unity comes in, because if the phase angle is 0, if the phase angle is 0, that would be 1. Cos of 0 is 1, and that's where we want the circuit to operate, in that area. Because in that situation you have, actually you're paying for what you're using. Right? Anything else is missing here? Yeah, if you wanted to write this in Kirchhoff's equation, you say B, like we said there, B1 plus B2 plus B3 is B. You could say VS here is BR plus BL plus BC, but you have to make sure you put these vectors on top of them, so that whoever reads this, they know this is not just algebraic sum of them. You can't just add them together. You have to do the vectorial sum. So we mentioned all that. Now, at that point where VL and VC are equal, or XL and XC are equal, or QL and QC are equal, which is what we want to do, what we want to have, we call that point resonant frequency. And that is where XL and XC are equal, basically. Right? That is your resonant frequency. At that frequency, because XL depends on 2 pi f L. Frequency, xc is also dependent on 2 pi f c. We can't change the capacitor, not all the time. We talked about banks of capacitor, having banks of capacitor and coming in and out. But at the end of the day, there are certain values. The capacitor is a certain value, inductor is a certain value. You can't go and change the values of it. But when you change the frequency, because they're dependent on frequency, if the frequency of the capacitor changes, or the circuit changes, sorry, the frequency goes up, the capacitive reactance comes down. Here, if the frequency goes up, inductive reactance goes up. So you'll have a frequency dependent for XL will be a line, and for XC it will be as the frequency increases, the XC decreases. At one point, XC and XL are equal. So this basically length and that is equal. This and this are equal. That is where the resonant frequency is. This frequency is resonant frequency, and we call that FO or F0. And if you equate this formula to this, because that's what we want to have XL to be equal with XC. So 2 pi FL equals 1 over 2 pi FC. You don't have to prove it, but this is how they proved where the formula comes from for the resonant frequency. 1 over 2 pi square root of LC. This is your resonant frequency formula. It is driven from here. If you work it out for frequency, if you transpose everything for frequency, you'll get to that. We don't want to prove that here.